Good morning, good afternoon, and good evening, everyone. So welcome again to this session where we will discuss on Hadoop interview questions, and we will learn on different aspects and be prepared for Hadoop interviews so that you can move into the big data arena. Here we have some list of questions and an explanation of those so that you can be well prepared for your Hadoop interviews. Now let's look at some general Hadoop questions. So what are the different vendor specific distributions of Hadoop? Now all of you might be aware that Hadoop or Apache Hadoop is the core distribution of Hadoop. And then you have different vendors in the market which have packaged the Apache Hadoop in a cluster management solution which allows everyone to easily deploy, manage, monitor, upgrade your clusters. So here are some vendor specific distributions. We have Cloudera, which is the dominant one in the market. We have Hortonworks, and now you might be aware that Cloudera and Hortonworks have merged. So it has become a bigger entity. You have MapR, you have Microsoft Azure, IBM's InfoSphere, and Amazon Web Services. So these are some popularly known vendor specific distributions. If you would want to know more about the Hadoop distributions, you should basically look into Google and you should check for Hadoop different distributions wiki page. So if I type Hadoop different distributions and then I check for the wiki page, that will take me to the distributions and commercial support page, and this basically says that the sole products that can be called a release of Apache Hadoop come from apache.org. So that's your open source community. And then you have various vendor specific distributions which basically are running in one or the other way Apache Hadoop, but they have packaged it as a solution like an installer so that you can easily set up clusters on set of machines. So have a look at this page and read through about different distributions of Hadoop. Coming back, let's look at our next question. So what are the different Hadoop configuration files? Now, whether you're talking about Apache Hadoop, Cloudera, Hortonworks, MapR, or no matter which other distribution, these config files are the most important and existing in every distribution of Hadoop. So you have Hadoop environment.sh, wherein you will have environment variables such as your Java path, what would be your process ID path, where will your logs get stored, what kind of metrics will be collected, and so on. Your core-site file has the HDFS path. Now this has many other properties like enabling thrash or enabling high availability or discussing or mentioning about your zookeeper. But this is one of the most important file. You have HDFS-site file. Now this file will have other information related to your Hadoop cluster, such as your replication factor, where will Namenode store its metadata on disk, if a data node is running, where would data node store its data? If a secondary name node is running, where would that store a copy of name node's metadata? And so on. Your MapRed-site file is a file which will have properties related to your MapReduce processing. You also have masters and slaves. Now these might be deprecated in a vendor specific distribution, and in fact you would have a YARN-site file which is based on the YARN processing framework which was introduced in Hadoop version 2, and this would have all your resource allocation and resource manager and node manager related properties. Again, if you would want to look at default properties for any one of these, for example, let's say HDFS-site file, I could just go to Google and type in one of the properties. For example, I would say dfs.namenode.name.directory, and as I know this property belongs to HDFS-site file, and if you search for this, it will take you to the first link which says HDFS default XML. You can click on this and this will show you all the properties which can be given in your HDFS-site file. It also shows you which version you are looking at, and you can always change the version here. So for example, if I would want to look at 2.6.5, I just need to change the version and that should show me the properties. Similarly, you can just give a property which belongs to say core-site file. For example, I would say fs.defaultfs, and that's a property which is in core-site file, and somewhere here you would see core minus default.xml, and this will show you all the properties. So similarly, you could search for properties which are related to yarn-site file or MapRed-site file. So I could say yarn.resource manager, and I could look at one of these properties, which will directly take me to yarn default XML, and I can see all the properties which can be given in yarn. And similarly, you could say MapReduce.job.reduces, and I know this property belongs to MapReduce-site file, and this takes you to the default XML. So these are important config files, and no matter which distribution of Hadoop you're working on, you should be knowing about these config files. Whether you work as a Hadoop admin or you work as a Hadoop developer, knowing these config properties would be very important, and that would also showcase your internal knowledge about the configs which drive your Hadoop cluster. Let's look at the next question. So what are the three modes in which Hadoop can run? So you can have Hadoop running in a standalone mode. Now that's your default mode. It would basically use a local file system and a single Java process. So when you say standalone mode, it is as you downloading Hadoop related package on one single machine, but you would not have any process running. That would just be to test Hadoop functionalities. You could have a pseudo distributed mode, which basically means it's a single node Hadoop deployment. Now Hadoop as a framework has many services. So it has a lot of services, and those services would be running irrespective of your distribution, and each service would then have multiple processes. So your pseudo distributed mode is a mode of cluster where you would have all the important processes belonging to one or multiple services running on a single node. If you would want to work on a pseudo distributed mode and using a Cloudera, you can always go to Google and search for Cloudera's Quick Start VM. You can download it by just saying Cloudera Quick Start VM, and you can search for this, and that will allow you to download a Quick Start VM, follow the instructions, and you can have a single node Cloudera cluster running on your virtual machines. For more information, you can refer to the YouTube tutorial where I have explained about how to set up a quick start VM. Coming back, you could have finally a production setup or a fully distributed mode, which basically means that your Hadoop framework and its components would be spread across multiple machines. So you would have multiple services such as HDFS, YARN, Flume, Scoop, Kafka, HBase, Hive, Impala, and for these services there would be one or multiple processes distributed across multiple nodes. So this is normally what is used in production environment. So you could say standalone would be good for testing, pseudo distributed could be good for testing and development, and fully distributed would be mainly for your production setup. Now, what are the differences between regular file system and HDFS? So when you say regular file system, you could be talking about a Linux file system, or you could be talking about a Windows-based operating system. So in regular file system, we would have data maintained in a single system. So the single system is where you have all your files and directories. So it is having low fault tolerance, right? So if the machine crashes, your data recovery would be very difficult unless and until you have a backup of that data. That also affects your processing. So if the machine crashes or if the machine fails, then your processing would be blocked. Now, the biggest challenge with regular file system is the seek time, the time taken to read the data. So you might have one single machine with huge amount of disks and huge amount of RAM. But then the time taken to read that data when all the data is stored in one machine would be very high, and that would be with least fault tolerance. If you talk about HDFS, your data is distributed. So HDFS stands for Hadoop Distributed File System. So here your data is distributed and maintained on multiple systems. So it is never one single machine. It is also supporting reliability. So whatever is stored in HDFS, say a file being stored, depending on its size, is split into blocks, and those blocks will be spread across multiple nodes. Not only that, every block which is stored on a node will have its replicas stored on other nodes. replication factor depends, but this makes HDFS more reliable. In cases of your slave nodes or data nodes crashing, you will rarely have data loss because of auto replication feature. Now, time taken to read the data is comparatively more, as you might have situations where your data is distributed across the nodes, and even if you are doing a parallel read, your data read might take more time because it needs coordination from multiple machines. However, if you are working with huge data which is getting stored, it will still be beneficial in comparison to reading from a single machine. So you should always think about its reliability through auto replication feature, its fault tolerance because of your data getting stored across multiple machines, and its capability to scale. So when you talk about HDFS, we are talking about horizontal scalability or scaling out. When you talk about regular file system, you are talking about vertical scalability, which is scaling up. Now, let's look at some specific HDFS questions. What is this? Why is HDFS fault tolerant? Now, as I just explained in previous slides, your HDFS is fault tolerant as it replicates data on different data nodes. So you have a master node and you have multiple slave nodes or data nodes where actually the data is getting stored. Now, we also have a default block size of 128 MB. That's the minimum since Hadoop version 2. So any file which is up to 128 MB would be using one logical block. And if the file size is bigger than 128 MB, then it will be split into blocks, and those blocks will be stored across multiple machines. Now, since these blocks are stored across multiple machines, it makes it more fault tolerant because even if your machines fail, you would still have a copy of your block existing on some other machine. Now, there are two aspects here. One, we talk about the first rule of replication, which basically means you will never have two identical blocks sitting on the same machine. And the second rule of replication is in terms of rack awareness. So if your machines are placed in racks, as we see in the right image, you will never have all the replicas placed on the same rack, even if they are on different machines. So it has to be fault tolerant and it has to maintain redundancy. So at least one replica will be placed on some other node on some other rack. That's how HDFS is fault tolerant. Now, here let's understand the architecture of HDFS. Now, as I mentioned earlier, you would in a Hadoop cluster, the main service is your HDFS. So for your HDFS service, you would have a name node, which is your master process running on one of the machines, and you would have data nodes, which are your slave machines getting stored across or the processes running across multiple machines. Each one of these processes has an important role to play. When you talk about HDFS, whatever data is written to HDFS, that data is split into blocks depending on its size, and the blocks are randomly distributed across nodes. With auto replication feature, these blocks are also auto replicated across multiple machines, with the first condition that no two identical blocks will sit on the same machine. Now, as soon as the cluster comes up, your data nodes, which are part of the cluster and based on config files, would start sending their heartbeat to the name node. And this would be every 3 seconds. What does Namenode do with that? Namenode will store this information in its RAM. So Namenode starts building a metadata in its RAM, and that metadata has information of what are the data nodes which are available in the beginning. Now, when a data writing activity starts and the blocks are distributed across data nodes every 10 seconds will also send a block report to Namenode. So Namenode is again adding up this information in its RAM, or the metadata in RAM, which earlier had only data node information. Now Namenode will also have information about what are the files. The files are split in which blocks, the blocks are stored on which machines, and what are the file permissions. Now, while Namenode is maintaining this metadata in RAM, Namenode is also maintaining metadata in disk. Now, that is what we see in the red box, which basically has information of whatever information was written to HDFS. So to summarize, your name node has metadata in RAM and metadata in disk. Your data nodes are the machines where your blocks or data is actually getting stored. And then there is a auto replication feature which is always existing unless and until you have disabled it. And your read and write activity is a parallel activity. However, replication is a sequential activity. Now, this is what I mentioned about when you talk about name node, which is the master process hosting metadata in disk and RAM. So when we talk about disk, it basically has a edit log, which is your transaction log, and your FS image, which is your file system image. Right from the time the cluster was started, this metadata in disk was existing, and this gets appended every time read, write, or any other operations happen on HDFS. Metadata in RAM is dynamically built every time the cluster comes up, which basically means that if your cluster is coming up, name node in the initial few seconds or few minutes would be in a safe mode, which basically means it is busy registering the information from data nodes. So name node is one of the most critical processes. If name node is down and if all other processes are running, you will not be able to access the cluster. Name node's metadata in disk is very important for name node to come up and maintain the cluster. Name node's metadata in RAM is basically for all or satisfying all your client requests. Now when we look at data nodes, as I mentioned, data nodes hold the actual data blocks and they are sending these block reports every 10 seconds. So the metadata in name node's RAM is constantly getting updated, and metadata in disk is also constantly getting updated based on any kind of write activity happening on the cluster. Now data node, which is storing the block, will also help in any kind of read activity whenever a client requests. So whenever a client or an application or an API would want to read the data, it would first talk to name node. Name node would look into its metadata on RAM and confirm to the client which machines could be reached to get to that data. That's where your client would try to read the data from HDFS, which is actually getting the data from data nodes. And that's how your read write requests are satisfied. Now, what are the two types of metadata in name node server holds? As I mentioned earlier, metadata in disk, very important to remember, edit log and FS image. Metadata in RAM, which is information about your data nodes, files being split into blocks residing on data nodes, and file permissions. So I will share a very good link on this, and you can always look for more detailed information about your metadata. So you can search for HDFS metadata directories explained. Now this is from Hortonworks. However, it talks about the metadata in disk, which name node manages, and details about this. So have a look at this link if you are more interested in learning about metadata on disk. Coming back, let's look at the next question. What is the difference between federation and high availability? Now these are the features which were introduced in Hadoop version 2. Both of these features are about horizontal scalability of name node. So prior to version 2, the only possibility was that you could have one single master, which basically means that your cluster could become unavailable if name node would crash. So Hadoop version 2 introduced two new features, federation and high availability. However, high availability is a popular one. So when you talk about federation, it basically means any number of name nodes. So there is no limitation to the number of name nodes. Your name nodes are in a federated cluster, which basically means name nodes still belong to the same cluster, but they are not coordinating with each other. So whenever a write request comes in, one of the name node picks up that request and it guides that request for the blocks to be written on data nodes. But for this, your name node does not have to coordinate with other name node to find out if the block ID which was being assigned was the same one as assigned by other name node. So all of them belong to a federated cluster. They are linked via a cluster ID. So whenever an application or an API is trying to talk to cluster, it is always going via an cluster ID, and one of the name node would pick up the read activity or write activity or processing activity. So all the name nodes are sharing a pool of metadata in which each name node will have its own dedicated pool. And we can remember that by a term called namespace or name service. So this also provides high fault tolerance. Suppose your one name node goes down, it will not affect or make your cluster unavailable. You will still have your cluster reachable because there are other name nodes running and they are available. Now when it comes to heartbeats, all your data nodes are sending their heartbeats to all the name nodes, and all the name nodes are aware of all the data nodes. When you talk about high availability, this is where you would only have two name nodes. So you would have an active and you would have a standby. Now normally in any environment you would see a high availability setup with Zookeeper. So Zookeeper is a centralized coordination service. So when you talk about your active and standby name nodes, election of a name node to be made as active and taking care of an automatic failover is done by your Zookeeper. High availability can be set up without Zookeeper, but that would mean that an admin's intervention would be required to make a name node as active from standby or also to take care of failover. Now, at any point of time in high availability, a active name node would be taking care of storing the edits about whatever updates are happening on HDFS, and it is also writing these edits to a shared location. Standby name node is the one which is constantly looking for these latest updates and applying to its metadata, which is actually a copy of whatever your active name node has. So in this way, your standby name node is always in sync with the active name node, and if for any reason active name node fails, your standby name node will take over and become the active. Remember, Zookeeper plays a very important role here. It's a centralized coordination service. One more thing to remember here is that in your high availability, secondary name node will not be allowed. So you would have an active name node and then you will have a standby name node which will be configured on a separate machine, and both of these will be having access to a shared location. Now that shared location could be NFS or it could be a quorum of journal nodes. So for more information, refer to the tutorial where I have explained about HDFS, high availability and federation. Now let's look at some logical question here. So if you have an input file of 350 MB, which is obviously bigger than 128 MB, how many input splits would be created by HDFS? And what would be the size of each input split? So for this, you need to remember that by default, the minimum block size is 128 MB. Now that's customizable. If your environment has more number of larger files written on an average, then obviously you have to go for a bigger block size. If your environment has a lot of files being written, but these files are of smaller size, you could be okay with 128 MB. Remember, in Hadoop, every entity, that is your directory on HDFS, file on HDFS, and a file having multiple blocks, each of these are considered as objects. And for each object, Hadoop's name node's RAM 150 bytes is utilized. So if your block size is very small, then you would have more number of blocks which would directly affect the name node's RAM. If you keep a block size very high, that will reduce the number of blocks, but remember that might affect in processing because processing also depends on splits. More number of splits, more the parallel processing. So setting of block size has to be done with consideration about your parallelism requirement and your name node's RAM which is available. Now coming to the question, if you have a file of 350 MB, that would be split into 3 blocks, and here 2 blocks would have 128 MB data, and the third block, although the block size would still be 128, it would have only 94 MB of data. So this would be the split of this particular file. Now let's understand about rack awareness. How does rack awareness work? Or why do we even have racks? So organizations always would want to place their nodes or machines in a systematic way. There can be different approaches. You could have a rack which would have machines running only master processes, and the intention would be that this particular rack could have higher bandwidth, more cooling, dedicated power supply, top of rack switch, and so on. The second approach could be that you could have one master process running on one machine of every rack, and then you could have other slave processes running. Now, when you talk about your rack awareness, one thing to understand is that if your machines are placed within racks, and we are aware that Hadoop follows auto replication, the rule of replication in a rack aware cluster would be that you would never have all the replicas placed on the same rack. So if we look at this, if we have block A in blue color, you will never have all the three blue boxes in the same rack, even if they are on different nodes, because that makes it less fault tolerant. So you would have at least one copy of block which would be stored on a different rack on a different node. Now let's look at this. So basically here we are talking about replicas being placed in such a way. Now somebody could ask a question, can I have my block and its replicas spread across 3 racks? And yes, you can do that, but then in order to make it more redundant, you are increasing your bandwidth requirement. So the better approach would be 2 blocks on the same rack on different machines and one copy on a different rack. Now let's proceed. How can you restart Namenode and all daemons in Hadoop? So if you were working on an Apache Hadoop cluster, then you could be doing a start and stop using Hadoop daemon scripts. So there are these Hadoop daemon scripts which would be used to start and stop your Hadoop. And this is when you talk about your Apache Hadoop. So let's look at one particular file which I would like to show you more information here. And this talks about your different clusters. So let's look into this. And so let's look at the start and stop. And here I have a file. Let's look at this one. And this gives you highlights. So if you talk about Apache Hadoop, this is how the setup would be done. So you would have it download the Hadoop tar file, you would have to untar it, edit the config files, you would have to do formatting, and then start your cluster. And here I have said using scripts. So this is in case of Apache Hadoop, you could be using a start all script that internally triggers start DFS and start YARN. And these scripts, start DFS, internally would run Hadoop daemon multiple times based on your configs to start your different processes. Then your start YARN would run YARN daemon script to start your processing related processes. So this is how it happens in Apache Hadoop. Now in case of Cloudera or Hortonworks, which is basically a vendor specific distribution, you would have say multiple services which would have one or multiple daemons running across the machines. Let's take an example here that you would have machine 1, machine 2 and machine 3 with your processes spread across. However, in case of Cloudera and Hortonworks, these are cluster management solutions. So you would never be involved in running a script individually to start and stop your processes. In fact, in case of Cloudera, you would have a Cloudera SCM server running on one of the machines and then Cloudera SCM agents running on every machine. If you talk about Hortonworks, you would have Ambari server and Ambari agent running. So your agents which are running on every machine are responsible to monitor the processes, send also their heartbeat to the master, that is your server, and your server is the one or a service which basically will give instructions to the agents. So in case of vendor specific distribution, your start and stop of processes is automatically taken care by these underlying services, and these services internally are still running these commands. However, only in Apache Hadoop you have to manually follow these to start and stop. Coming back, we can look into some command related questions. So which command will help you find the status of blocks and file system health? So you can always go for a file system check command. Now that can show you the files for a particular HDFS path. It can show you the blocks, and it can also give you information on status such as under replicated blocks, over replicated blocks, misreplicated blocks, default replication, and so on. So your FSCK file system check utility does not repair if there is any problem with the blocks, but it can give you information of blocks related to the files, on which machines they are stored, if they are replicated as per the replication factor, or if there is any problem with any particular replica. Now, what would happen if you store too many small files in a cluster? And this relates to the block information which I gave some time back. So remember, Hadoop is coded in Java. So here every directory, every file and file related block is considered as an object. And for every object within your Hadoop cluster, Namenode's RAM gets utilized. So more number of blocks you have, more would be usage of Namenode's RAM. And if you're storing too many small files, it would not affect your disk. It would directly affect your Namenode's RAM. That's why in production clusters, admin guys or infrastructure specialists will take care that everyone who is writing data to HDFS follows a quota system so that you could be controlled in the amount of data you write plus the count of data an individual writes on HDFS. Now, how do you copy data from local system onto HDFS? So you can use a put command or a copy from local and then give in your local path, which is your source, and then your destination, which is your HDFS path. Remember, you can always do a copy from local using a -f option. That's a flag option, and that also helps you in writing the same file or a new file to HDFS. So with your -f, you have a chance of overwriting or rewriting the data which is existing on HDFS. So copy from local or -put, both of them do the same thing, and you can also pass an argument when you're copying to control your replication or other aspects of your file. Now, when do you use DFS admin refresh nodes or RM admin refresh nodes? So as the command says, this is basically to do with refreshing the node information. So your refresh nodes is mainly used when, say, a commissioning or decommissioning of nodes is done. So when a node is added into the cluster or when a node is removed from the cluster, you are actually informing Hadoop master that this particular node would not be used for storage and would not be used for processing. Now in that case, you would be, once you are done with the process of commissioning or decommissioning, you would be giving these commands, that is refresh nodes and RM admin refresh nodes. So internally, when you talk about commissioning, decommissioning, there are include and exclude files which are updated. And these include and exclude files will have entry of machines which are being added to the cluster or machines which are being removed from the cluster. And while this is being done, the cluster is still running. So you do not have to restart your master process. However, you can just use these refresh commands to take care of your commissioning, decommissioning activities. Now, is there any way to change replication of files on HDFS after they are already written? And the answer is, of course, yes. So if you would want to set a replication factor at a cluster level, and if you have admin access, then you could edit your HDFS-site file, or you could say Hadoop-site file. And that would take care of replication factor being set at a cluster level. However, if you would want to change the replication after the data has been written, you could always use a setrep command. So setrep command is basically to change the replication after the data is written. You could also write the data with a different replication, and for that you could use a -d dfs.replication and give your replication factor when you're writing data to the cluster. So in Hadoop, you can let your data be replicated as per the property set in the config file. You could write the data with a different replication. You could change the replication after the data is written. So all these options are available. Now, who takes care of replication consistency in a Hadoop cluster? And what do you mean by under, over replicated blocks? Now, as I mentioned, your fsck command can give you information of over or under replicated blocks. Now, in a cluster, it is always and always Namenode which takes care of replication consistency. So for example, if you have set up a replication of 3, and since we know the first rule of replication, which basically means that you cannot have 2 replicas residing on the same node, it would mean that if your replication is 3, we would need at least 3 data nodes available. Now say for example, you had a cluster with 3 nodes and replication was set to 3. At one point of time, one of your name node crashed. And if that happens, your blocks would be under replicated. That means there was a replication factor set, but now your blocks are not replicated, or there are not enough replicas as per the replication factor set. This is not a problem. Your master process or name node will wait for some time before it will start the replication of data again. So if a data node is not responding, or if a disk has crashed, and if name node does not get information of a replica, name node will wait for some time and then it will start re-replication of those missing blocks from the available nodes. However, while name node is doing it, the blocks are in under replicated situation. Now when you talk about over replicated, this is a situation where name node realizes that there are extra copies of block. Now this might be the case that you had 3 nodes running with a replication of 3. One of the node went down due to a network failure or some other issue. Within few minutes, name node re-replicated the data, and then the failed node is back with its set of blocks. Again, name node is smart enough to understand that this is a over replication situation, and it will delete set of blocks from one of the nodes. It might be the node which has been recently added, it might be your old node which has joined your cluster again, or any node. That depends on the load on a particular node. Now we discussed about Hadoop, we discussed about HDFS. Now we will discuss about MapReduce, which is the programming model, and you can say processing framework. What is distributed cache in MapReduce? Now we know that when we talk about MapReduce, the data which has to be processed might be existing on multiple nodes. So when you would have your MapReduce program running, it would basically read the data from the underlying disks. Now this could be a costly operation if every time the data has to be read from disk. So distributed cache is a mechanism wherein data set or data which is coming from the disk can be cached and available for all worker nodes. Now how will this benefit? So when a MapReduce is running, instead of every time reading the data from disk, it would pick up the data from distributed cache, and this will benefit your MapReduce processing. So distributed cache can be set in your job conf, where you can specify that a file should be picked up from distributed cache. Now let's understand about these roles. So what is a record reader, what is a combiner, what is a partitioner, and what kind of roles do they play in a MapReduce processing paradigm or MapReduce operation. So record reader communicates with the input split, and it basically converts the data into key value pairs. And these key value pairs are the ones which will be worked upon by the mapper. Your combiner is an optional phase. It's like a mini reduce. So combiner does not have its own class. It relies on the reducer class. Basically, your combiner would receive the data from your map tasks which would have completed, works on it based on whatever reducer class mentions, and then passes its output to the reducer phase. Partitioner is basically a phase which decides how many reduce tasks would be used, aggregate or summarize your data. So partitioner is a phase which would decide based on the number of keys, based on the number of map tasks. Your partitioner would decide if one or multiple reduce tasks would be used to take care of processing. So either it could be partitioner which decides on how many reduce tasks would run, or it could be based on the properties which we have set within the cluster, which will take care of the number of reduce tasks which would be used. Always remember, your partitioner decides how outputs from combiner are sent to reducer and to how many reducers. It controls the partitioning of keys of your intermediate map outputs. So map phase, whatever output it generates is an intermediate output, and that has to be taken by your partitioner or by a combiner and then partitioner to be sent to one or multiple reduce tasks. This is one of the common questions which you might face. Why is MapReduce slower in processing? So we know MapReduce goes for parallel processing. We know we can have multiple map tasks running on multiple nodes at the same time. We also know that multiple reduce tasks could be running. Now why does then MapReduce become a slower approach? First of all, your MapReduce is a batch oriented operation. Now, MapReduce is very rigid and it strictly uses mapping and reducing phases. So no matter what kind of processing you would want to do, you would have to still provide the mapper function and the reducer function to work on data. Not only this, whenever your map phase completes, the output of your map phase, which is an intermittent output, would be written to HDFS and thereafter underlying disks. And this data would then be shuffled and sorted and picked up for reducing phase. So every time your data being written to HDFS and retrieved from HDFS makes MapReduce a slower approach. The question is, for a MapReduce job, is it possible to change the number of mappers to be created? Now, by default, you cannot change the number of map tasks because number of map tasks depends on the input splits. However, there are different ways in which you can either set a property to have more number of map tasks which can be used, or you can customize your code or make it use a different format which can then control the number of map tasks. By default, number of map tasks are equal to the number of splits of file you are processing. So if you have a 1 GB of file that is split into 8 blocks of 128 MB, there would be 8 map tasks running on the cluster. These map tasks are basically running your mapper function. If you have hard-coded properties in your mapred-site file to specify more number of map tasks, then you could control the number of map tasks. Let's also talk about some data types. So when you prepare for Hadoop, when you want to get into big data field, you should start learning about different data formats. Now there are different data formats such as Avro, Parquet, you have sequence file or binary format, and these are different formats which are used. Now when you talk about your data types in Hadoop, these are implementation of your writable and writable comparable interfaces. So for every data type in Java, you have a equivalent in Hadoop. So int in Java would be int writable in Hadoop, float would be float writable, long would be long writable, double writable, boolean writable, array writable, map writable, and object writable. So these are your different data types that could be used within your MapReduce program. And these are implementation of writable and writable comparable interfaces. What is speculative execution? Now imagine you have a cluster which has huge number of nodes and your data is spread across multiple slave machines or multiple nodes. Now at a point of time, due to a disk degrade or network issues or machine heating up or more load being on a particular node, there can be a situation where your data node will execute task in a slower manner. Now in this case, if speculative execution is turned on, there would be a shadow task or another similar task running on some other node for the same processing. So whichever task finishes first will be accepted and the other task would be killed. So speculative execution could be good if you are working in an intensive workload kind of environment, where if a particular node is slower, you could benefit from a unoccupied or a node which has less load to take care of your processing. Going further, this is how we can understand. So node A, which might be having a slower task, you would have a scheduler which is maintaining or having knowledge of what are the resources available. So if speculative execution as a property is turned on, then the task which was running slow, a copy of that task, or you can say a shadow task, would run on some other node, and whichever task completes first will be considered. This is what happens in your speculative execution. Now, how is identity mapper different from chain mapper? Now, this is where we are getting deeper into MapReduce concepts. So when you talk about mapper, identity mapper is the default mapper which is chosen when no mapper is specified in MapReduce driver class. So for every MapReduce program, you would have a map class which is taking care of your mapping phase, which basically has a mapper function and which would run one or multiple map tasks, right? Your program would also have a reduce class, which would be running a reducer function, which takes care of reduce tasks running on multiple nodes. Now, if a mapper is not specified within your driver class, so driver class is something which has all information about your flow. What's your map class? What is your reduce class? What's your input format? What's your output format? What are the job configurations and so on? So identity mapper is the default mapper which is chosen when no mapper class is mentioned in your driver class. It basically implements an identity function which directly writes all its key pairs into output. And it was defined in old MapReduce API in this particular package. But when you talk about chaining mappers or chain mapper, this is basically a class to run multiple mappers in a single map task. Or basically you could say multiple map tasks would run as a part of your processing. The output of first mapper would become as an input to second mapper and so on. And this can be defined in the undermentioned class or package. What are the major configuration parameters required in a MapReduce program? Obviously, we need to have the input location. We need to have the output location. So input location is where the files will be picked up from, and this would preferably on HDFS directory. Output location is the path where your job output would be written by your MapReduce program. You also need to specify input and output formats. If you don't specify, the defaults are considered. Then we need to also have the classes which have your map and reduce functions. And if you intend to run the code on a cluster, you need to package your class in a jar file, export it to your cluster, and then this jar file would have your mapper, reducer, and driver classes. So these are important configuration parameters which you need to consider for a MapReduce program. Now, what is the difference, or what do you mean by map side join and reduce side join? Map side join is basically when the join is performed at the mapping level or at the mapping phase, or is performed by the mapper. So each input data which is being worked upon has to be divided into same number of partitions. Input to each map is in the form of a structured partition and is in sorted order. So map side join, you can understand it in a simpler way that if you compare it with RDBMS concepts where you had two tables which were being joined, it will always be advisable to give your bigger table as the left side table or the first table for your join condition, and it would be your smaller table on the left side and your bigger table on the right side, which basically means the smaller table could be loaded in memory and could be used for joining. So map side join is a similar kind of mechanism where input data is divided into same number of partitions. When you talk about reduce side join, here the join is performed by the reducer. So it is easier to implement than map side join, as all the sorting and shuffling will send the values or send all the values having identical keys to the same reducer. So you don't need to have your data set in a structured form. So look into your map side join or reduce side join and other joins just to understand how MapReduce works. However, I would suggest not to focus more on this because MapReduce is still being used for processing, but the amount of MapReduce based processing has decreased overall or across the industry. Now, what is the role of output committer class in a MapReduce job? So output committer, as the name says, describes the commit of task output for a MapReduce job. So we could have this as mentioned, org Apache Hadoop MapReduce output committer. You could have a class which extends your output committer class. So MapReduce relies on this. MapReduce relies on the output committer of the job to set up the job initialization, cleaning up the job after the job completion. That means all the resources which were being used by a particular job, setting up the task temporary output, checking whether a task needs a commit, committing the task output, and discarding the task out. So this is a very important class and can be used within your MapReduce job. What is the process of spilling in MapReduce? What does that mean? So spilling is basically a process of copying the data from memory buffer to disk when obviously the buffer usage reaches a certain threshold. So if there is not enough memory in your buffer, in your memory, then the content which is stored in buffer or memory has to be flushed out. So by default, a background thread starts spilling the content from memory to disk after 80% of buffer size is filled. Now, when is the buffer being used? So when your MapReduce processing is happening, the data is being read from the disk, loaded into the buffer, and then some processing happens. Same thing also happens when you are writing data to the cluster. So you can imagine for a 100 megabyte size buffer, the spilling will start after the content of buffer reaches 80 megabytes. This is customizable. How can you set the mappers and reducers for a MapReduce job? So these are the properties. So number of mappers and reducers, as I mentioned earlier, can be customized. So by default, your number of map tasks depends on the split, and number of reduce tasks depends on the partitioning phase, which decides number of reduced tasks which would be used depending on the keys. However, we can set these properties either in the config files or provide them on the command line, or also make them part of our code, and this can control the number of map tasks or reduce tasks which would be run for a particular job. Let's look at one more interesting question. What happens when a node running a map task fails before sending the output to the reducer? So there was a node which was running a map task, and we know that there could be one or multiple map tasks running on one or multiple nodes, and all the map tasks have to be completed before the further stages that such as combiner or reducer come into existence. So in a case if a node crashes where a map task was assigned to it, the whole task will have to be run again on some other node. So in Hadoop version 2, YARN framework has a temporary daemon called application master. So your application master is taking care of execution of your application. And if a particular task on a particular node failed due to unavailability of node, it is the role of application master to have this task scheduled on some other node. Now, can we write the output of MapReduce in different formats? Of course we can. So Hadoop supports various input and output formats. So you can write the output of MapReduce in different formats. So you could have the default format, that is text output format, wherein records are written as line of text. You could have sequence file, which is basically to write sequence files or your binary format files, where your output files need to be fed into another MapReduce jobs. You could go for a map file output format to write output as map files. You could go for a sequence file as a binary output format. So that's again a variant of your sequence file input format. It basically writes keys and values to a sequence file. So when we talk about binary format, we are talking about a non-human readable format. DB output format. Now, this is basically used when you would want to write data to, say, relational databases or, say, NoSQL databases such as HBase. So this format also sends the reduce output to a SQL table. Now, let's learn a little bit about YARN. YARN, which stands for Yet Another Resource Negotiator. It's the processing framework. So what benefits did YARN bring in Hadoop version 2, and how did it solve the issues of MapReduce version 1? So MapReduce version 1 had major issues when it comes to scalability or availability because, in Hadoop version 1, you had only one master process for processing layer, and that is your job tracker. So your job tracker was listening to all the task trackers which were running on multiple machines. So your job tracker was responsible for resource tracking and job scheduling. In YARN, you still have a processing master, but that's called resource manager instead of job tracker. And now with Hadoop version 2, you could even have resource manager running in high availability mode. You have node managers which would be running on multiple machines, and then you have a temporary daemon called application master. So in case of Hadoop version 2, your resource manager or master is only handling the client connections and taking care of tracking the resources. the jobs scheduling, or basically taking care of execution across multiple nodes, is controlled by application master till the application completes. So in YARN, you can have different kind of resource allocations that could be done, and there is a concept of container. So container is basically a combination of RAM and CPU cores. YARN can run different kind of workloads. So it is not just MapReduce kind of workload which can be run on Hadoop version 2, but you could have graph processing, massive parallel processing, you could have real-time processing, and huge processing applications could run on a cluster based on YARN. So when we talk about scalability, in case of your Hadoop version 2, you can have a cluster size of more than 10,000 nodes and can run more than 100,000 concurrent tasks. And this is because for every application which is launched, you have this temporary daemon called application master. So if I would have 10 applications running, I would have 10 app masters running, taking care of execution of these applications across multiple nodes. Compatibility. So Hadoop version 2 is fully compatible with whatever was developed as per Hadoop version 1, and all your processing needs would be taken care by YARN. So dynamic allocation of cluster resources, taking care of different workloads, allocating resources across multiple machines and using them for execution, all that is taken care by YARN. Multi-tenancy, which basically means you could have multiple users or multiple teams. You could have open source and proprietary data access engines, and all of these could be basically hosted using the same cluster. Now, how does YARN allocate resources to an application with the help of its architecture? So basically, you have a client or an application or an API which talks to resource manager. Resource manager is, as I mentioned, managing the resource allocation in the cluster. When you talk about resource manager, you have its internal two components. One is your scheduler and one is your applications manager. So when we say resource manager being the master is tracking the resources, resource manager is the one which is negotiating the resources with slave. It is not actually resource manager who is doing it, but these internal components. So you have a scheduler which allocates resources to various running applications. So scheduler is not bothered about tracking your resources or basically tracking your applications. So we can have different kind of schedulers such as FIFO, which is first in first out. You could have a fair scheduler or you could have a capacity scheduler. And these schedulers basically control how resources are allocated to multiple applications when they are running in parallel. So there is a queue mechanism. So scheduler will schedule resources based on requirements of application, but it is not monitoring or tracking the status of applications. Your applications manager is the one which is accepting the job submissions. It is monitoring and restarting the application masters. So it's application manager which is basically then launching a application master which is responsible for an application. So this is how it looks. So whenever a job submission happens, we already know that resource manager is aware of the resources which are available with every node manager. So on every node which has fixed amount of RAM and CPU cores, some portion of resources, that is your RAM and CPU cores, are allocated to node manager. Now resource manager is already aware of how much resources are available across nodes. So whenever a client request comes in, resource manager will make a request to node manager. It will basically request node manager to hold some resources for processing. Node manager would basically approve or disapprove this request of holding resources. And these resources, that is a combination of RAM and CPU cores, are nothing but containers. We can allocate containers of different sizes within yarn-site file. So your node manager, based on a request from resource manager, guarantees the container which would be available for processing. That's when your resource manager starts a temporary daemon called application master to take care of your execution. So your app master, which was launched by resource manager, or we can say internally by applications manager, will run in one of the containers, because application master is also a piece of code. So it will run in one of the containers, and then other containers will be utilized for execution. This is how YARN is basically taking care of your allocation. Your application master is managing resource needs. It is the one which is interacting with scheduler, and if a particular node crashes, it is the responsibility of app master to go back to the master, which is resource manager, and negotiate for more resources. So your app master will never ever negotiate resources with node manager directly. It will always talk to resource manager, and resource manager is the one which negotiates the resources. Container, as I said, is a collection of resources like your RAM, CPU, network bandwidth, and your container is allocated based on the availability of resources on a particular node. So, which of the following has occupied the place of a job tracker of MapReduce? So, it is your resource manager. So, resource manager is the name of the master process in Hadoop version 2. Now, if we would have to write yarn commands to check the status of an application, so we could just say yarn application minus status and then the application ID. And you could kill it also from the command line. Remember, your yarn has a UI, and you can even look at your applications from the UI. You can even kill your applications from the UI. However, knowing the command line commands would be very useful. Can we have more than one resource manager in a yarn based cluster? Yes, we can. That is what Hadoop version 2 allows us to have. So you can have a high availability yarn cluster where you have an active and standby, and the coordination is taken care by your zookeeper. At a particular time, there can only be one active resource manager, and if active resource manager fails, your standby resource manager comes and becomes active. However, zookeeper is playing a very important role. Remember, zookeeper is the one which is coordinating the server state, and it is doing the election of active to standby failover. What are the different schedulers available in YARN? So you have a FIFO scheduler, that is first in, first out, and this is not a desirable option, because in this case, a longer running application might block all other small running applications. Your capacity scheduler is basically a scheduler where dedicated queues are created and they have fixed amount of resources. So you can have multiple applications accessing the cluster at the same time, and they would be using their own queues and the resources allocated to them. If you talk about fair scheduler, you don't need to have a fixed amount of resources. You can just have a percentage, and you could decide what kind of fairness is to be followed, which basically means that if you were allocated 20 gigabytes of memory, however, the cluster has 100 gigabytes, and the other team was assigned 80 gigabytes of memory, then you have 20% access to the cluster, another team has 80%. However, if the other team does not come up or does not use the cluster, in a fair scheduler, you can go up to maximum of 100% of your cluster. To find out more information about your schedulers, you could either look in Hadoop definitive guide, or what you could do is you could just go to Google and you could type, for example, yarn scheduler. Let's search for yarn scheduler, and then you can look in Hadoop definitive guide. And so this is your Hadoop definitive guide, and it beautifully explains about your different schedulers, how do multiple applications run, and that could be in your FIFO kind of scheduling, it could be in capacity scheduler, or it could be in a fair scheduling. So have a look at this link. It's a very good link. You can also search for yarn untangling, and this is a blog of this is a series of 4 blogs where it's beautifully explained about your yarn, how it works, how the resource allocation happens, what is a container, and what runs within the container. So you can scroll down, you can be reading through this, and you can then also search for part 2 of it, which talks about allocation and so on. So coming back, we basically have these schedulers. What happens if a resource manager fails while executing an application in a high availability cluster? So in a high availability cluster, we know that we would have two resource managers, one being active, one being standby, and zookeeper, which is keeping a track of the server states. So if a RM fails in case of high availability, the standby will be elected as active, and then basically your resource manager or the standby would become the active one. And this one would instruct the application master to abort in the beginning. Then your resource manager recovers its running state. So there is something called as RM state store, where all the applications which are running, their status is stored. So resource manager recovers its running state by looking at your state store, by taking advantage of container statuses, and then continues to take care of your processing. Now, in a cluster of 10 data nodes, each having 16 GB and 10 cores, what would be total processing capacity of the cluster? Take a minute to think. 10 data nodes, 16 GB RAM per node, 10 cores. So, if you mention the answer as 160 GB RAM and 100 cores, then you went wrong. Now think of a cluster which has 10 data nodes, each having 16 GB RAM and 10 cores. Remember, on every node in a Hadoop cluster, you would have one or multiple processes running. Those processes would need RAM. The machine itself, which has a Linux file system, would have its own processes. So that would also be having some RAM usage, which basically means that if you talk about 10 data nodes, you should deduct at least 20 to 30% towards the overheads, towards the Cloudera based services, towards the other processes which are running. And in that case, I could say that you could have 11 or 12 GB available on every machine for processing, and say 6 or 7 cores. Multiply that by 10, and that's your processing capacity. Remember, the same thing applies to the disk usage also. So if somebody asks you, in a 10 data node cluster where each machine has 20 terabytes of disks, what is my total storage capacity available for HDFS? So the answer would not be 200. You have to consider the overheads. And this is basically which gives you your processing capacity. Now let's look at one more question. So what happens if requested memory or CPU cores beyond or goes beyond the size of container? Now, as I said, you can have your configurations which can say that in a particular data node which has 100 GB RAM, I could allocate say 50 GB for the processing. Out of 100 cores, I could say 50 cores for processing. So if you have 100 GB RAM and 100 cores, you could ideally allocate 100 for processing, but that's not ideally possible. So if you have 100 GB RAM, you would go for 50 GB, and if you have 100 cores, you would go for 50 cores. Now within this RAM and CPU cores, you have the concept of containers, right? So container is a combination of RAM and CPU cores. So you could have a minimum size container and maximum size container. Now at any point of time, if your application starts demanding more memory or more CPU cores, and this cannot fit into a container allocation, your application will fail. Your application will fail because you requested for a memory or a combination of memory and CPU cores which is more than the maximum container size. So look into this yarn tangling website which I mentioned, and look for the second blog in those series which explains about these allocations. So these are some important interview questions which we discussed today. So you should look into these questions, search for their answers again. Might be if you can capture and gain some external information, it will always be useful. And basically, you can learn more by practicing these questions. So keep learning, keep practicing these questions, and you can always search in Google for the links which I mentioned, which have more details on these topics, especially YARN, your MapReduce, and your HDFS related commands. Look into these blogs which I shared with you, and look into the metadata path to have a good and a fair understanding of your metadata which is stored by your name node in its RAM and in its disk. Take care, all the best.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.